When a wire forms a circuit that connects the positive terminal of a battery to its negative terminal, current flows from the positive terminal to the negative terminal. This is due to the electromotive force of the battery, and we sometimes say that the battery pushes the current through the wire. The battery actually sets up an electric field in the wire, and we know that charges in electric fields experience forces. The current that the battery can push through a wire is analogous to the water flow that a pump can push through a pipe. Greater pump pressures lead to larger water flow rates, and similarly, greater battery voltages lead to larger electric currents. In the simplest case, the current I in the electric circuit is directly proportional to the voltage V. Thus, a voltage of 12 volts leads to twice as much current as a voltage of 6 volts when each is connected to the same circuit. Finally, current actually flows through a battery, just as the water in the pipe circuit must flow through the pump. There are a few things to note about the circuit shown here. First, no charge flows, or there is no current if there is a break in the circuit. In other words, the circuits must be a complete loop. Next, the battery forces all of the electrons in the circuit to move simultaneously. That is, the charges move in the upper segments and all of the other segments the instant the battery is connected. You can visualize this if you imagine that the pipes shown here are completely filled with water with no air gaps. The instant you turn on the pump, the water in all parts of the pipe move at the same time. In a water pipe, the flow rate is not only determined by the pump pressure, but is also affected by the length and diameter of the pipe. Longer and narrower pipes offer higher resistance to the moving water and lead to smaller flow rates for a given pump pressure. For instance, if we make one segment of the pipe very narrow, it offers a stronger resistance to the flow than the wide pipe. A similar situation exists in electric circuits, and to deal with it, we need to introduce the concept of electrical resistance. We can make it more difficult for current to flow through a part of a circuit if we replace a section of the wire with a material that doesn't conduct electricity as well. These electrical elements are called resistors, and are usually given the symbol R in circuit diagrams as shown here. So now our water analogy of an electric circuit is complete. Wires are like pipes, resistors are like narrow pipes, and batteries are like pumps. We'll find later that this water and pipe analogy is helpful to describe other circuit phenomena. Electrical resistance is defined in terms of two ideas that we have already discussed: the electric potential difference, or voltage, and the electric current. The resistance R is defined as the ratio of the voltage applied across a piece of material to the current I through the material, or R equals V divided by I. When only a small current results from a large voltage, there is a high resistance to the moving charge. For many materials, such as metals, the ratio V divided by I is the same for a given piece of material over a wide range of voltages and currents. In such a case, the resistance is constant. In this case, the relation R equals V divided by I is referred to as Ohm's law, after the German physicist George Simon Ohm, who discovered it in the early 1800s. Ohm's law is stated as follows: the ratio V divided by I is a constant, where V is the voltage applied across a piece of material, such as a wire, and I is the current through the material. This is expressed mathematically as R equals V divided by I, which equals a constant, or V equals IR, where R is the resistance of the piece of material. The SI unit of resistance is the volt per ampere, which is defined as the ohm, and given the symbol omega. We'll soon see how Ohm's law can be applied to find resistances, currents, and voltages in practical circuits. Consider this circuit. The circuit elements that you see here are standard, and you will see them in various combinations in all circuits. We will add some new ones later when we learn about capacitors and inductors. Going clockwise around the circuit, we have a battery, a wire segment. By the way, all lines connecting circuit elements are assumed to be wires, a resistor with resistance R, and a switch, which behaves like a wire when it is closed, as shown here. It acts like a broken circuit when it is open, and in this case, no current could flow. That's basically what a switch does. Like when you turn off a light in your house, it breaks the circuit. Now, suppose that the battery has a voltage of V equals 12.0 volts across its terminals, and the resistor has a value of R equals 220 ohms. What is the current through this circuit? First, note that the current, whatever its value, goes clockwise around the circuit because current flows from the positive terminal of the battery to the negative terminal. Next, we apply Ohm's law to find the current. We have I equals V divided by R, which equals 12.0 volts divided by 220 ohms, which equals 0.05 volts per ohm, which equals 0.05 amperes. In summary, Ohm's law is stated as follows. The ratio V divided by I is a constant, where V is the voltage applied across a piece of material, such as a wire, and I is the current through the material. This is expressed mathematically as V equals I times R, where R is the resistance of the piece of material. The SI unit of resistance is the volt per ampere, which is defined as the ohm and given the symbol omega.